All right, we're starting with Unit 6, oblique triangles. And let's see, understand the 4 possible cases in trying to solve an oblique. Let's get clear about what an oblique triangle is. We've been working throughout this semester with right triangles. We've been doing right triangle trig. It's a great way to learn trig. And now we're talking about triangles which have no right angles. So you could say every triangle is either right, it's either a right triangle, or it's not a right triangle. If it's not a right triangle, another way I could say it is an oblique triangle. So that's all we mean when we say oblique. We'll get to the law of sines later. Today we're just going to talk about 4 cases. We're going to start with geometry. This is so basic, isn't it? 6 parts. We've got 3 sides, 3 angles. The size and shape are completely determined by fixing only 3 of these parts, provided they're the right 3. What would be the wrong 3? Angle, angle, angle. So the wrong 3 would be, for example, angle, angle, angle. I could have a right isosceles triangle. There it is. All the angles are the same. Excuse me, I haven't even drawn the second one yet. All the angles are known here. This is 45, 45, 90. And then I could have an isosceles right triangle, again, 45, 45, 90. But the size has varied, right? Because I'm relying strictly on angles, I really can't completely determine that triangle. But there are some ways that we can. We can figure it with angle, angle, side, angle, side, angle, side, angle, side, and of course side, side, side. You studied these in geometry. There are 2 others that we know don't work. This one here, which we can say they're similar, but we have no idea about their size comparisons. And SSA, we're going to talk about this one a lot. This is called the ambiguous case. Sometimes it determines a triangle, and sometimes it doesn't. We need something like that to sort of spice things up, don't we? With trig, we can find the other parts of a triangle once congruence is established. The tools we use would be the law of sines, the law of cosines. This is from another text, so that doesn't make any sense. Okay, oblique triangles. Any triangle which is not a right triangle is oblique. We can fully determine a triangle if we know the length of its sides. We can fully determine a triangle if we have the included sides. We've got angle on one end of the side and the angle on the other end. Or we could have, see, in both cases we've got 2 angles in the side. So as long as we have 2 angles in the side, whether it's included or not included between the angles, we can determine the triangle. We can solve it. The other one that works every time is when you have an included angle. between the two known sides. Those will always work for us. Here's the one that is considered ambiguous, and let me show you what happens here. We have a just checking, make sure that was in place. Let me move it back. Okay. Here we have an angle, but it's not an included angle, and two sides. This is always ambiguous, and I'll show you why. We could have a side. Let me see if I can move this, which is too short to ever form. See, that would be our best shot right there, and doesn't make a triangle. So, too short to ever form a triangle. We could have a side which is just right. I'm supposed to be keeping its length always the same. Just right to form one triangle. It can't do more than that because here it's too long to connect. So this one will form just one triangle, and this one formed a triangle over on that side, and as I go around, it will form a triangle here. So we could have, in the case of the two sides without an included angle, we could have 0 triangles, 1 triangle, or 2 triangles. Let's review labeling. I think we've done this before. We've got A, let's review labeling. The vertices are capital letters, A, B, C. Our opposite sides, opposite C is side C, opposite A, side A. And notice those are lowercase. Then for the measures of the angles, we use alpha, beta, and gamma. Those are the Greek letters that correspond with A, B, and C. We're going to derive the law of sines here. In this oblique triangle, we can always, and do, don't we? To figure the altitude, we drop a line from the vertex above at perpendicular to the base. We refer to this as the height or the altitude of the triangle. If I look at sine of alpha, it would be opposite over the hypotenuse, right? Because we're looking at the right triangle here. Opposite, which is H, over the hypotenuse, which is C. If I look at the sine of gamma, it's opposite, which is H, over hypotenuse, but in the case of this triangle, the hypotenuse is A. I can solve for H in both of these, right? This one will be C times sine of alpha, and this one will be A times sine of gamma. All right, so H and H are obviously the same here. They're equal to one another. So if two things are equal to a third item, then they are equal to each other, aren't they? So I can say C times sine of alpha equals A times sine of gamma. And having said that, I could divide both sides by C, in which case this will cancel out. I'll have sine of alpha equals A sine gamma divided by C. And now suppose I divide both of these by A. And when I do so, that will cancel out. And voila, I have the law of sines. And it is so easy to remember. I love this law. Sine of alpha over short side A, they match. Sine of beta over short side B, and sine of gamma over short side C. Now, of course, I've shown all three of the sides, and I only demonstrated this part of this equality. Because actually, I could do it again to prove to you how beta fits in. So we've got a proportion here that can help us solve many triangles. Let's see if we can solve this one. We'll demonstrate what we do with this. Solve the triangle. Approximate to the nearest tenth. I'd like you, when you do this, to set up a little table of your angle measures and your side lengths. Those are the 6 things you need to know to be able to say that you solved the triangle. And some of them will be given, but just seeing where those givens fall in this little table will help you do your solution. Do we have alpha? Yes, we do. It's 36 degrees. Do we have beta? Yes, we do. It's 48 degrees. Do we have gamma? No, we're going to have to find that.